Welcome back, everyone. This is Professor Herring. In this video, we're going to learn about molecular composition. Specifically, we're going to learn about molecular and empirical formulas, how to convert between mass and moles and number of particles, as well as determining the molecular weight of a compound, the percent of a given element of a compound, and using those combined with the empirical formula to find the molar mass. Up until this point, we've talked about atoms. We've talked about protons, electrons, and neutrons and how they combine together to form atoms and elements. But it turns out that there's very few elements that exist only as atoms. Those are really only the noble gases, and not even all of the noble gases will exist solely as atoms. In other words, almost every single element on the periodic table prefers to form bonds. And when they do this, they form what are called molecules or compounds. When we look at molecules, there's a couple different subcategories. We can have homonuclear diatomic molecules, which means that it is one element, but two of that element. So this might be hydrogen, fluorine, oxygen, etc. You need to be familiar with these homonuclear diatomic molecules. And in high school chemistry, you might have learned the following mnemonic, which is Hofbrinkel. And Hofbrinkel tells you the identities of the diatomic elements that you need to be familiar with. Hydrogen, oxygen, fluorine, bromine, nitrogen, and there's an I in there, iodine, and chlorine. Then we have heteronuclear diatomic molecules, which means that there's two atoms and two elements. That could be hydrogen chloride, hydrogen fluoride, carbon monoxide, or many other things. A third subcategory of these molecules is polyatomic molecules. And these are molecules that consist of a single type of element, but more than two of them. So in other words, ozone, O3, has a single element, oxygen, but there's three of them. And we also have phosphorus, which exists as a P4 molecule. Diamond can exist in carbon structures that have hundreds and thousands of carbons. Let's see here. There we go. So diamond can exist as carbon 50, really anything up to essentially on the atomic scale an infinite number of carbon atoms. But it turns out that so while we have diatomic and triatomic or polyatomic molecules, really most elements exist as compounds. And a compound is where we have at least three atoms of at least two different types of elements. Some examples of this include water, methane, and ammonia, and these make up examples of what are called molecular compounds. Ionic compounds consist of things such as calcium oxide, scandium nitride, sodium nitrate, potassium oxide, and the difference is that with molecular compounds, you have very discrete molecules of a certain size. Water always exists as H2O. Methane always exists as CH4, and ammonia always as NH3. With ionic compounds, you have complex three-dimensional structures that are up to millions and millions of atoms long and wide. And these are much more diverse in terms of their sizes and their shapes than molecular compounds. Molecular compounds, they consist of nonmetals that are bound to each other. Nonmetals are found on the right side of the periodic table, and we've looked at this already. The one exception to that, depending on which periodic tables you look at, is hydrogen. Hydrogen is on the left side of the periodic table typically, but it is also one of the nonmetals. So when you have combinations of these nonmetals that are bound together, they form what are called molecular compounds. To contrast with this, we have ionic compounds. And ionic compounds consist of metal cations that are bound to nonmetal anions. Metals are found on the left side of the periodic table, generally speaking, and those could be alkali metals, alkaline earth metals, transition metals. You could also have lanthanoids and actinoids. The metalloids, it turns out, can behave similarly to both metals and nonmetals, depending on their context. We're not going to go into great detail about them in Chem 110. One exception to this rule of metals binding to nonmetals making ionic compounds is the ion ammonium. When you take a look at ammonium, it is consisting completely of nonmetals, nitrogen and hydrogen. However, because it has a positive charge, it behaves like a metal within compounds. Now that we've laid the groundwork for compounds, both molecular and ionic compounds, let's talk about chemical formulas. So each molecule has its own chemical formula, and we have different ways of representing this. The most simple way is called the empirical formula. This gives the lowest whole number ratio of each kind of atom, and that should be kind, each kind of atom in a substance. So if we could have a ratio of 1 carbon to 2 hydrogens to 1 oxygen, and that, because we cannot reduce it any smaller and still maintain that ratio, that's an empirical formula. However, we can expand that and take a look at an actual molecule. This one here is ribose. Ribose, you'll notice, has the same empirical formula as the molecule above. In other words, if we reduce this down by 5, we get C, H2, and then O. Ribose here is a sugar that's present in DNA and other things. If we wanted to represent this in a structural way to show how the atoms are bounded, it might look like the following. And so what we see is that there are different ways of representing molecules. A given molecular formula represents, in writing, the actual molecules themselves, but it does not represent the structure, the way that they're bound. We're going to look more at that in Chapter 6, but I wanted to give you a picture of what that might look like here with the structural formula. And so there's a relationship between the empirical and the molecular formulas. It's a whole number relationship. In this case, for ribose, it's a factor of 5, but it really could be any factor, including 1. In other words, there is a molecule that exists with the molecular formula CH2O as well. Something to note about ionic compounds is that they're really extended networks in 3 dimensions, and we talk about them having a formula unit as opposed to a molecular unit. There's no real difference between the empirical and molecular formula, and so we always write them with their lowest whole number ratio. So for example, this would be calcium oxide, CaO. We would never write it anything beyond that, Ca2O2 or anything higher. You know, you're never going to write out Ca100 O2 100. You always maintain the lowest whole number ratio for ionic compounds. Now that we have an idea of what a molecular formula is, we can use that molecular formula to calculate what are called molar masses. These are also sometimes called molecular or molar weights. And this is the sum of the atomic mass of each atom within the compound, or if it's an ionic compound, within the formula unit. And these we can find using the periodic table by taking the average atomic mass of each element and summing them together. We've talked about before that the periodic table shows the atomic masses, the average atomic mass in AMU and grams per mole. we're going to leave the AMU behind at this point in the semester and focus really more on grams per mole because we're getting into more large-scale chemicals. So if we wanted to calculate the molecular weight for ribose, the way that we would do this is one way you could do this is split it up into each component element and then take the number of a given element, the number within a compound, multiplied by the atomic mass or the molar mass of said element from the periodic table. That looked like the following. For carbon, we have 5 carbon atoms per molecule. Each carbon weighs 12.01 grams per mole. When we multiply those together, we get that the total mass of carbon in ribose is 60.05 grams. For hydrogen, there are 11 hydrogen. Excuse the typo there. That should be 10. And that gets a total of 10.10 grams of hydrogen. Oxygen, there are 5 oxygen with a molar mass of 16 grams per mole, giving us 80 grams of hydrogen. When we multiply all of this together, we get 150.16 grams per mole for ribose. You could repeat this process for any compound given its molecular formula. Simply multiply the molar mass of a given element times the number of that element within a compound. We also need to know how to convert between different units. So we already looked at converting between particles and moles by using Avogadro's number. Well, we can use the molar mass to convert from moles to grams, and that's going to be the focus of this chapter. A final set of ideas that we need to understand is percent composition. And that is essentially the mass percent of each element within a compound. And so if we know the molecular or empirical formula of a compound, the percent mass can be determined by dividing essentially the factor of a given element divided by the total molecular mass. So in the case of we'll take a look at a molecule in a minute, but when we looked at ribose, we had 5 carbons. And if we multiply that by the atomic weight of each carbon and divide by the total molar mass, then we can find the percentage of the carbon within the total, which is approximately, let's rewrite this, (60 grams per mole over 150 grams per mole, which is approximately, let's see here, doing this in my head, 35% by mass. And we can also use, if we know the mass, or to find the mass percent, if we know the fraction of that sample within the total. And so to show you what that looks like in 2 different cases, here's the sample problem. If we're given ammonium nitrate, we want to know what's the percent composition of nitrogen. We can use this equation where we look at the mass percent by comparing it by multiplying the number of a given element times its atomic weight and divide by the total molecular weight of the compound. Mass percent of nitrogen would be found by multiplying 2, because there's 2 nitrogens in the compound, times 14 grams per mole, which is its atomic weight, divided by 80 grams per mole, and multiply by 100. And this gets us approximately 35% nitrogen. The way that we found the 80 grams per mole was by adding together by adding together the atomic masses of the components that make up the ammonium nitrate. Mass percent hydrogen and oxygen are also given, and what we should see is that they add up to be 100% total. Another way of looking at this is perhaps you know what mass of each you're given and you want to know the mass percent. This can be found by taking the ratio of the mass of a given element by its total percent. And in this case, we're given that we've got 28.9% oxygen and 54.3% total, or 54.3 grams total of sample. So to calculate the mass percent of oxygen, we can take the 28.9 grams of oxygen, divide by the 54.3 grams in our sample, and multiply by 100% to get 53.2% oxygen. So that's it for this video. In the next video, we're going to look at calculating using the empirical molecular formulas in relation to each other. Thanks for watching. If you have any questions, be sure to ask on Piazza, in office hours, or at your recitation. Have a good day.